Hi, my name is Jim, and I'd like to talk about power in an AC circuit. And we're going to start with three different scenarios. One is a voltage source and a resistor of 5 ohms, and the second is the same voltage across a capacitive reactance of negative J 5 ohms, and the third is the same voltage across an inductance of plus J 5 ohms. Now, there's three different measurements when we talk about power, and one is P, and the unit is watts. You're used to that. And the second is S, and S is measured in volt amperes. So the unit is going to be VA, and volt ampere simply means in any circuit, it's the product of the voltage and the current that's flowing. It doesn't have anything to do or tell us about the actual power, if any, that's dissipated in the circuit. And the third case is referred to as reactive power. Its symbol is Q, and the unit is volt ampere reactive. So that will be the power that isn't dissipated in a reactance. Now, in every case here, this is considered to be pure, and that leads to some problems. Specifically, divide by 0, undefines, and if we take the limit of that, we end up with infinities. But I've not drawn any limiting resistors in here, so we can just deal with these circuits. And I only say that to be complete and let my conscience be at ease. So if we start with power in a resistive circuit, it's simply 10 volts, 5 ohms, 2 amperes is flowing. 2 amperes times 10 volts is 20 watts. Well, 2 amperes times 10 volts is also 20 volt amperes. But since 0 power is being stored, the VAR expressed in Q equals something VAR would be 0. So this isn't storing anything. It's dissipating 20 watts. Now, if we go over to the capacitive circuit, 100% of the power that's absorbed when the capacitor is charging is discharged when it, is returned when it's discharging. So the net power that a capacitor dissipates is 0 watts. It means in English, it doesn't get hot. Current flowing through the circuit is still 20 volt amperes because we have 10 volts RMS and 5 ohms reactive. And how much is the reactive power? How much is stored and returned? Well, that's going to be 20 volt ampere reactive. So we could say Q equals 20 VAR. Lastly, if we look at the inductive circuit, it's storing energy in a magnetic field part of the time and then returning it. So the power it dissipates is 0 watts. Now we're assuming that there's 0 ohms winding resistance and 0 ohms everywhere else. The current flowing in the circuit's the same, 20 volt amperes, and this is storing energy in a magnetic field, and then when the magnetic field collapses, it returns that energy. So that would be Q equals 20 VAR. Now we're going to get into this in more detail later with what's called the power triangle. But for now, my purpose is basically this dissipates power, this is 0, and that's 0. So in any situation, if you're asked what the power is, and you're given circuits like this, the calculations, well, there aren't any. Just write down 0. Look at a couple examples here. Suppose I have T equals 510 sine of 2 pi times 7050, that would be in hertz, T minus 55 degrees milliamperes peak. And we want to find VP and the voltage peak and voltage RMS if the current is flowing through a resistor that produces 4 watts. Now, we've got a little difficulty here because 4 watts, since it doesn't say its peak power, is assumed to be average power. And here we're dealing with MA peak. So we have to be very careful about that in our calculations. So once we notice this, that we're dealing with the current in peak, and the second is that the 4 watts is assumed to be P average because it's not stating that it's P peak. So then we can go ahead and solve this, and there's first thing you need to do is eliminate the noise. And the noise in the circuit for power would be frequency components. Power is not a function of frequency, and the offset. Power is not a function of the offset either. So what we're interested in here is this term. Now, could have said 510 milliamperes peak, but it's better to say it this way so you know that this isn't going to contribute to the power dissipation. So there's several ways to start, or several approaches, so I'm just using one of them. And I began by converting the current into RMS. So the current flowing I in RMS is equal to 0.707 times I peak, which is 510 milliamperes, which gives us 361 milliamperes RMS. And I'm being very careful to subscript this correctly. My next step is find the power. P equals V times I. So we have VRMS is going to be basically P average divided by I RMS. We just calculated that. 4 watts divided by 361 milliamperes RMS will give us 11.08 volts RMS. So if we're working with average power and RMS current, we're going to get RMS voltage. And contrarily, if we're working with peak power and peak current, we would be getting peak voltage. Now all this doesn't matter because you can convert one into the other very easily. So next, let's take a look at, let's see here, V peak. So I calculated him, and he turns out to be 1.414 times VRMS. Remember that this 1.414 is 1 divided by the square root of 2. And it's much easier just to memorize a number than it is to do that. 1 divided by 0.707 is 1.414. So that's 1.414 times 11.08 volts RMS gives us 15.67 volts peak. Next, to find the peak power, well, peak power is the average power times 2, and that would be equal to 2 times 4 watts, which would be 8 watts. Peak. It's important that I put that there. And then finally, the resistance would be equal to VRMS over IRMS, or V peak over I peak. And using the peaks here, as that comes out to be 30.72 ohms. So the ratio of these two in RMS, and both have to be in RMS, is the same as the ratio of the peak, and they both have to be in peak. So that's one example. Let's look at one more. And V of t is equal to 18 sine of 49.2 K, and the units there would be hertz. And this is omega. That's the radian frequency. 2 pi times F times T, and this time we don't have any offset. And this voltage is appearing across the 15 ohm resistor, and our mission is to find everything. So let's do that. Several approaches, and they all yield different approaches can yield a correct answer. So I chose to find the peak power first. Since I have the peak voltage, it's simply equal to V peak squared divided by R, which comes out to be 21.6 watts peak. And this time I didn't forget the peak. P equals P average. So if average isn't there and you see a P, you assume that it's P average is equal to P peak divided by 2. 21.6 watts peak divided by 2 is 10.8 watts. And I don't have to say average, although I could if I wanted to. Next, VRMS is we're given 18 volts peak, so that's 0.707 V peak. and that comes out to be 12.73 VRMS. And then I just got so carried away with this red pen that I calculated V peak again. 18.0 volts, already have it, so, you know, what can I tell you? And then, well, it's good it came out to be 18 volts, I suppose. I peak, and I chose to use V peak over R, and that would be 18.0 divided by 15 ohms, gives us 1.20 amperes peak. Finally, IRMS is equal to 707, 0.707 times I peak, and that gives us 848 milliamperes RMS. So, suppose we had a circuit like this, and this is a little bit more complicated because we've got an R that dissipates power and an impedance ZC, which is just in polar form, that would be the magnitude at negative 90 degrees. It doesn't dissipate power, so our steps to solve this would be a little bit different. First, we'd find Z total, nothing new there. Then, using voltage divider, find the voltage across the resistor, and then once we know that, to find the power in the resistor, it's simply the voltage across the resistor squared divided by R. Now, if you're doing this in V peak, the power you're going to get is going to be in P peak. So to find the average power on that, you just divide P peak by 2. So that's it for a quick overview on power, and thank you for watching.